Good evening, everyone. So we are continue for the rest part of this week. So we'll talk about uninformed search strategies. So for this one, the most important thing I want to mention about is the project. So although I have released the announcement today, but I want to enhance in case you miss it, correct? So for this one, I just changed. For initially, so if you turn this one, you just want to implement some both uninformed and informed search algorithm. So the algorithm is in the available algorithm is in the page 2. Initially, we have depth first search, breadth first search, and greedy best first search, and then a star search. So you need to select one from the group 1 and then one from group 2. But just today I realized greedy best first search is just like a early version, maybe it's like an unimproved version of a star. So that means because this one is only look at the future cost, not look at the past cost. So that means a star and this one are correlated to each other too much. For example, if you just select these two, the difficulty level will be dropped. So I think that will be not fair for other people who select depth first search or breadth first search, and then a star, of course, you must implement. So that means that's why I just deleted this one, since this if you know a star search, greedy best first search is just like a downgraded version of a star search. So that means it should be easy to code, to program. So that's why I just decided today by deleting this one, and then you must select one from these two. So depth first search and breadth first search will be covered by this lecture, okay, this video. And then a star search will be covered by next week. So till next week, you will be able to finish all the content of project 1, okay, project assignment 1. Okay, just want to raise your attention. So this is the only changes I have made for this PA1. Okay, I think this will be the last version. I don't know. Usually I didn't change project. Yeah, but this time maybe just consider this issue. So for fairness, I decided to change rather than just leaving it like that. Okay, thanks for your understanding, and then please just remember using this latest version, select one from depth first or breadth first search. Just select one, either one, okay? And then you must implement a star search. So that's one, you need to implement 2 search algorithms in this project. Okay, do it early. I think the difficulty level is not that much because you have a lot of reference code, especially here. Okay, we'll help you. You can utilize the code, but not copy the code. You can refer to it, but do not just copy. Okay, I want to see your own analysis. You need to write a report, detail your understanding and your design, your data structures, your algorithms, your running results, your findings, what you have learned from this one. Okay? I hope you can implement independently if it's possible. Okay, maybe after you implement it, and then you can compare to see whether you can do some optimization or you confirm the catalyst of your implementation. Okay, do not look at the code right away in the beginning. Okay, but maybe they also have some difference. Okay, because this is for our project, will not be the same as the code provided here. This one maybe provides some general implementation about the A star, depth first, and the breadth first search, but you need to accommodate to this maze, and also you have different mazes to explore, different mazes to explore. So that means you also need to use my design the cost function as well. Okay, and also the heuristic function mentioned, use the Manhattan distance. So Manhattan distance, if you don't know, just search on website. That means block distance. Just like you want to go to from one building to the other building, you cannot take the diagonal cut. You must take the block distance. For example, like this one, you have building, and then you have another building here. So you must go along this way, rather than just go directly. Okay? That's the distance. You add this one and this one. So that's called the block distance or Manhattan distance. Okay, that's the first thing I want to mention, and then let's continue for this part. So for this one, we in the previous slides and the videos, we already mentioned the previous slide and video. Already mentioned about we have a strategy, how to develop a search strategy. So we know we use the frontier, and then we expand the frontier, and then we select one node from the frontier to confirm whether it's go or not, go test. If it's not, of course we need to remove it anyway. Remove from the frontier and then test, go test, and then expand its successors into the frontier. So the next thing is that how to select a node from the frontier. This will have a most important impact on your algorithm's performance. Whether you can get the optimal solution, your time, your efficiency, your optimality, your completeness. Later we talk about this completeness. So that means if there's a solution, whether you can find it. Optimality, that means if you found a solution, whether this one is the optimal. So, and whether it's time consuming, what's the complexity, like these things. Okay, this will depending on your search strategy. Okay, search strategy. So here is just like defined by picking the order of node expansion. That means how to pick a node for next expansion, next go test. So we have two types. The first type we covered in this slide, and then the next informed one we covered in the next. So like the greedy best first search and the A* search, that will be the informed. Okay. So uninformed search means you only have the problem itself. You don't have any prior information. That means you don't have any hint. Okay, you don't have any hint. Only know the problem itself. For example, I just tell you, for example, from Long Beach to New Orleans, but I didn't tell you what's the for example location of New Orleans. For example, what's the straight distance between New Orleans and Long Beach, between any cities, in between, right? For example, St. Louis, okay? What's that one? Just forgot. Okay, some cities, okay? For example, like a study center or some location, some cities or some important points. So that means I didn't tell you what's the straight line distance between these. This straight line distance will help you. For example, this is the goal. This is the starting position state. So you may visit this one. And then if you know this information, that will help you to guide your search. If I don't tell you this information, you only have what? You only have the connections. Okay, you know the cities connected like this way. So you don't have that straight line distance. So that's only the problem itself, kind of like the Romania problem. You only have that graph, that route kind of map. So you only can use that map. I didn't tell you what's the straight distance between any two cities. Then you cannot use that one, right? Okay, if like that, that will be the uninformed. That means only the problem itself, without any hint, any prior information, any prior. Okay. So if for this one we have such 4 algorithms which will be covered in these slides. The first one is called breadth first search, depth first search, and then we have iterative deepening search. So iterative deepening search is a modification or improved version of DFS, for depth first search. And then another one is we further improve, we propose uniform code search. Uniform code search is just deal with another group. So you can think about this one where you only deal with some type 1, but this one will deal with type 2. So that means if later you find out type 1 is just like each code, step code is the same, but type 2 may be different. If like that, we need to consider uniform code search. Okay, so although you have learned maybe BFS, DFS before, but maybe we have some different implementation here. For example, you may learn the algorithms needed in algorithms, maybe also in data structures, right? But it will be handled for some special problem like a graph search. But here is just like a general one. Okay, it doesn't have to be a graph, but I just tell you we use this approach. Okay, so breadth first search. Let's look at the first one. Since it is breadth first search, so if we can generate a search tree, right? Is search tree, so must explore all the nodes in the one layer. After you finish all the nodes in that layer, you can continue with the next layer, because that's the breadth. That means make it as long as you can find a node in that layer, you need to explore. Okay, explore the whole, and then till you exhaust all of the nodes in that layer, you can continue with the next layer. So this is the idea. So expand shallowest unexpanded node. So that means this is a criteria for you to select the node to do the goal test and expansion. So you will find the shallowest in the frontier, okay? In the frontier, and also unexpanded. Of course, you knew the frontier will only keep the unexpanded node. Okay, how to implement this one? So since we added the nodes to the frontier based on the layer by layer, so one layer first, and then we expand this node. We select one node, expand its successor. That means it should be the next layer, okay? So for example, you have layer 1, and then you select this one, and then it has some children, okay? Successors. So if you add it in the next, so you must visit the same layer nodes, okay? All the 4 nodes in the layer 1, and then you can continue layer 2, layer 3. So that means we can use you can find here, we insert the next successors or new frontier nodes in the end, and then every time we select the first, the previous or the oldest node which had been inserted into the data structure. So that's like based on the time they arrive, okay? First arrived, first served, or first in, first out, okay? First come, first serve. So if we use, for example, maybe operating system, we have first come, first served. But for here, with first in, first out. So first in, first out, the easiest one to implement this mechanism is a queue. Okay? We queue in a queue. Okay, we queue in a queue, and then based on the order, we order for the arrival time to be scheduled, to be selected as the next node to be doing the goal test and expansion. Okay, so this is the idea. Let's look at this example. For example, this one is an example state space graph for a tiny search problem. For example, this is a starting state, this is goal state, and then it's a directed graph. So if there's an arrow, that means it's reachable from the source to destination. So this is the successor. Okay, for this one. So how to use a queue to implement the BFS algorithm here. So BFS, we said that we need to insert the nodes layer by layer. So that's easy, right? So from here, you draw an arc, and then you can find, of course, because this is directed graph. So that means all the arrows out. Okay, this we can say degree out, degree in. So this is degree out. So must go into other nodes. That will be the next layer. Okay, so this one, and this one. So DEP, okay, is the next layer, and then you based on the alphabetical order. So so draw an arc again, okay, and then it will have this one is not, because this is in, okay. Well, you want to find out 1, B, C, and E. So E again will be considered, but you need to do the explored set detection. Okay, is already explored, so you may need to only update the path. So whether this path is closer than this one. Okay, if closer, you need to replace the new E. Okay, this new E with the old E, old E with the new E. The new E has maybe the new node. Okay, we said new node, that will be different because the parent is different. Parent here is D. This parent is S. So that will be different. And then so on and so forth. Okay, so you insert B, C, and then in the end, and then E to test the path. So this is the basic idea. Let's look at its details. So for simplicity, we just expand that graph, or rewrite the graph layer by layer. Kind of layer 1, layer 2, layer 3, layer 4, layer 5, and so on and so forth. Okay? So that means from S you have D, E, and P. That's correct. Okay? And then D, we just mentioned about you have B, C, E. Okay, you need to put that B, C, E there, because this is just only show. So when we do explore, we also have B, C, E. Okay? And then from E, you draw an arc, draw a circle. Anyway, that's the same. Okay? So to R to H, that's only cut. So from E, R, H, so on and so forth. Okay? So on and so forth. And then from here, the E is also H to R, but you can find this HR and this HR not the same layer. Okay? But you still need to do like that. This one just show you, for example, if you expand, what will be the order for the nodes to be inserted? Or you can think about this is the expansion order. Okay, expansion order. Okay. So this expansion order S, D, E, P, and then B, C, E, H, R, Q. Okay. So here we may just use the alphabetical order P, Q. Okay, P, Q, F, C, G. So they use the alphabetical order to list the children under the same parent. Okay, use the alphabetical order. Okay, same. This is easy. Okay, this is just like this. So that means we know how to expand. So that means the first time we have S, and based on S we have expansion. So we have this frontier, and then we explore the first one, remove it from the frontier to see whether it's the goal G. No, it's not a goal G. Okay? So we need to expand. We add a B, C, E in the end of the Q. Okay, and then continue for the next one. We are not continue with this B, C, E. We need to continue with the E is not the goal state G, so we need to expand it again. So H and R. So every time if you want to insert one, you need to test whether it's already there or not. That's why you can find here. So here, when we add this one, we need to test because you already add E, so you don't need to add E again, but you need to test whether this distance is smaller than SE. So SDE, the total distance, whether it's less than this one. Don't worry, because for this node already have that information. Each time if you visit a node, you will record the path as well, because based on the parent you can reconstruct the path. So that's the E, to test this one and this one to see which one is smaller. So this is how we do the breadth first search. So in a word, just explore nodes layer by layer, layer by layer. This is layer by layer. So this is the idea. Let's look at the second one, is depth first search. What's the difference between this one and the previous one? Depth first search is different from breadth first search. Breadth first search is layer by layer, but depth first search, if you can go further, you just go till you cannot find a node to explore. For example, you already reached the leaf node, and then you have to go back, and then only go back one layer, and then to see whether you have some other parent children, and then if you can go further, then go further, and then can go further till you cannot go further. You reach the leaf node, and then go back one more layer, one layer above, and then explore whether there's some additional siblings, and then go layer deeper and deeper if you can go. So this is the idea. So yes, maybe one branch you already reach with all of them, then maybe you go back, retract till you reach the front. That's what's possible. Just like this. Go further if you can go. If you don't have any node, you go one more, and then to see whether the children, there's some sibling. If you can go further, you can go further. If you cannot, go back till you go to here, and then there's the other siblings. Go further till you cannot go, and then see whether there's some other siblings. If no, go back. So this is till you find all the, you have visited all the nodes, or you have found the goal. So here we have one concern, because we said we don't have to assume the problem is discrete. Maybe you have even it's discrete, you may have infinite many nodes to explore in one direction. So this has a concern. So just like you're doing research, what will be the optimal? So once algorithm, maybe there's no dead end to reach the optimality. It can be always find something to improve. So like this, you will go further and further till forever. You may don't have a chance to go back, because you always can go deeper. So this is the problem with depth first search. Maybe you cannot find the optimal solution. If you have infinite many nodes in some branches, and you are taking that branch, taking that route, if you have a path, along that path there's infinite many nodes to explore, but you also just use that path to explore the algorithm, then you may just you may just get lost. Finally, you used all the time, but cannot find the solution. Okay. So the implementation for this one is using the go back, maybe expand the deepest. So the difference is previous one is layer by layer. So shallowest first. So BFS. But for this one is the deepest first. Which one has the deepest depth? We'll take that one and then make it further. So just like you dig a hole, if you can dig further, just dig further. But breadth first search, we may just do sampling. So one layer, and then second layer, deeper, all of the layers deeper. So this is like we can cover more possibilities. But the depth first search will just explore the depths, make it deeper and deeper. So of course, if the solution is very deep, this maybe have some good chance to get the optimal solution quickly. But if, for example, if the answer is just like in the rightmost sibling, but you go deeper and deeper, this will just do nothing. If you use breadth first search, you can find the answer very quickly, because you just maybe need to go with 1 or 2 layers more, then you can find the solution. Okay, so this is like a risky. Okay, so anyway, this is the totally different. That one is the shallow based. This one is the deepest first. And then also we use different mechanism to implement. So the previous one, we use the queue, first in, first out queue. So here we use last in, first out queue. The reason is that we want to save the current state, and then we explore the current one, and then if we find some new one, we insert in the end, but we still continue, so that we explore further and further till we reach the last, or just forever. So this is the last in, first out, or first in, last out. Anyway, it's still queue. So last in, first out, the queue, is a stack. So this one means we want to use a stack. So you push the nodes you have found before. For example, in the previous layers, layer 1, okay, push in the bottom of the stack, and then if you have some new nodes push on top of this one, that means they are the newer. They will be explored first, and then explore the previous layers. So that means every time you explore the deepest layer first. Okay, so this is the last in, first out. Still the same problem. Let's look at for this one how we explore the nodes in this one. Still this one, and then we still the same graph. Okay, we draw like this way. So this is like the search graph. That means we ignore the arrow here, but this one is like we can only go down, cannot go up. Okay? So you can find here we explore this way. First one we find S, and then D, and then B, and then A. If we cannot find anything, we have to go back, and then C and A, and then go back, and then E, and then H, and then P, and then Q, and then go back, and then Q, and then go back, and then R, F, C, A, and then go back, and then G, and then go back to her, and then continue just like this way. So this is how we explore the depth first search. Okay, so you can find the difference. So this one is just like if you can find a node to explore and then go further to explore it till you reach some leaf node, you can return. So assume you have a leaf node you can return. If you don't have, you may have trouble for this algorithm. So the expansion order you can find here is D, B, A, just like what I'm right, C, and then A again, and then E, and then H, P, Q, and then Q again, and then E is already explored. And then if you meet a node, just explore it, and then R, F, C, A, and then finally find G. Yeah, I need to stop. This one is already there. So you find the goal state. So if for example, the node is in some deeper layers, this one may have some advantage. You can find here, because layer by layer you have to expand you have to explore all the layers, and then you can reach here. So the time complexity, you need just compare how many nodes you explored, you visited. If you can visit less nodes to reach the goal, that of course is the preferred algorithm. Okay, so this is the idea. So mechanism, just use a stack. The preferred one we use a queue. Okay. So this one show one example. For example, you have a date with your girlfriend, and then you are a person which is very perfect. Okay. Perfect person means we consider a lot of things, and then we want to explore many things. So we prefer deep thinking, but we may cannot have whole control on the overall things. Okay, like this one. So preparing for a date. What situations might I prepare for? The first one is medical emergency. The second one is dancing, and the third one is food too expensive. Okay. But in fact, maybe dancing should be more important. Okay, but just you happen to list the first one. Okay, and then maybe we exhaust your time, and then let's see what happened. So medical emergency. Okay, what kind of emergency can happen? The first one is A, snake bite, and then B is lightning strike. C is fall from chair. Okay, and then we need to explore the first one along this list. Okay, so deeper and deeper. Emergency, snake bite, and then which snake are dangerous? Let's see. A, corn snake. B, garter snake. C, corpse snake. Maybe a long list as well. And then you have another question about these snakes. So because this is dangerous, but the research comparing snake venoms is scattered and inconsistent. I will make a spreadsheet to organize it. Okay, and then finally you are done, right? And then your girlfriend is already arrived here to pick you up, but you haven't dressed. Okay, and by this one, what's this meaning? I'm not quite sure. LD 50, maybe some, yeah, but some reference. Okay, LD, and then the inland taipan has the deadliest venom of any snake. Okay, I think maybe your girlfriend will be feel interesting about your word. What happened to you? And then maybe something will happen next. So I really need using depth first search, so you can explore more. This is just show you like a demo or just like a story to teach you like a very easy way to understand what is depth first search. So use a practical problem, right? So use the basic idea is just like you are very picky, you want to take care of everything, and then you have a long list, so each one must be perfect. Okay, you will explore each one, study each one, doing research each one. So maybe a good thing that you need to use this okay, use this attitude for your study, for your work, but maybe use breadth first search use for your life. That will be better, right? Because you need to handle so many things. And for this one is for your subject, for your professional development, maybe better, right? Focus on one project, one AI course, and one major, one subject, like this. Okay. So anyway, this is the basic idea. Okay, let's look at the analysis. So we use these things to evaluate the algorithm. So we already mentioned some of them. So that means we have many, even the uninformed one. Okay, we have many choices So which one will be the best? So usually we use criteria, or you call it evaluation matrix. So here we use this evaluation matrix, which is very, very common, to think. For example, you want to search. What we want to know is that first, whether you can find the solution, if there's a solution, and how fast you can approach to the solution, like these things. Okay, and then something more. Let's look at the first one. Is a completeness. Completeness means does it always find a solution if one exists? That's what I mentioned. If there's a solution there, whether your approach can guarantee to find that solution. Just think about breadth first search and the depth first search. We said depth first search maybe is risky, if you just like that one, like the dating one, if like that one, I think maybe you cannot finish the whole task because you haven't exhausted all the items in that task list. So just the reason. For example, if you explore one direction till you reach the end, but you haven't found anything there, and then you don't have time. Or you can just go very far till forever. You cannot have a time, cannot have a chance to go back to explore some other branches which have some solutions. Maybe optimal, maybe not optimal. Some solutions. Sometimes not only one. So that's why we say we have an optimal solution, the second one. So optimality, that means that if you found a solution, whether this solution is the best or not, whether you can guarantee this one is the best. So what is the optimal solution? So we need to understand for search algorithm like this one, we have a search tree. So optimal solution, because we decide the optimality based on the path from the starting node to that solution, solution node, state solution node. So the path means the path, because you will go from one layer to the other layer, because we will arrange them by layer. So that means the depths will decide. The depths will decide the optimality. We prefer the shallowest. Is it correct? The shallowest solution will be the best. Is it correct? Shallowest. So that means from the starting state node to reach that solution, the path is the minimum. So whether your solution can find that one, the shallowest solution in the minimum time, will decide whether your algorithm is optimal or not. So that's your optimality virtue or property criteria. We use this one. Okay. So that means if there's an answer, whether you can guarantee to find an answer. If you find an answer where this is optimal, and the next one is that if you can find the answer which is also optimal, and assume they have the answer which is optimal, find an existing optimal answer, how long does it take for you to find, for your algorithm to find that answer? This is the complexity. Usually for algorithm we have these two things, so time efficiency and space efficiency. So that's the two important things. Usually we consider these two. Okay, that's for any algorithm. So this one is special for this optimization problem, because it's like a search. You want to find an optimal solution. So we need to find this completeness and optimality. So time complexity is the number of nodes generated. Because we said we have a large state space. We cannot first illustrate all of them. We generate all the state space. So that's why we use a practical way. We generate nodes when necessary. So if you generate more nodes, that means it takes more time, because you need to explore them, save them, So that means this is means explored. Okay, of course, if you generate a node, then you know what is the node. So number of nodes visited will be the time complexity. Okay, total number of nodes that have been visited or generated will be the time complexity. And the next one is the space complexity. So that means we want to save the nodes temporarily, right? So that's maximum number of nodes in memory. So that means at most, right, you need to create a space to hold this number of nodes in the memory. You may need to think about the border, right, upper bound. So that means at some time, maybe you need to save this number of nodes. Okay. So we here define several items or several variables to represent some important information for the search algorithm. So later we use these several items to indicate the time complexity and the space complexity. Of course, we also check or examine the completeness and the optimality of an algorithm. Let's look at the first variable is b. B is branching. B is for branching vector. Okay, branching vector, that means from one node, how many children, right? So this one is the maximum. That means some trees have a lot of branches. So the maximum number of branches it has, that a search tree has, that will be the B. Why we use this one? Because this will be used to consider the bound. Okay, that at most has this number of children. Okay, only B number of children. And then next one is D and M. D and M maybe sometimes you will confuse, but if you use the letter to correspond, it should be easy for you to remember. So M is the maximum, D is the depth. So if we can find the optimum, because we are concerned about the optimality, right? So whether you can reach that optimal solution, because maybe some algorithm is the optimal, and then they can reach that optimality. So optimality, where is the optimal solution? So D is used to represent the depth of the optimal solution. So that means D. So from a tree till this, you will find the first optimal solution. Maybe in this layer you have multiple optimal, but this one maybe just the smallest. You can think about the smallest, maybe the share the smallest. So this is the smallest depth to find the optimal solution. That means the shallowest layer which has the solution. Correct? So this is the meaning for D. D for depth of the optimal or shallowest. So they're same, right? Because we said if it's optimal, must be shallowest. And then M is the maximum length. So M is maximum length. We indicate this M. So for example, you will explore the tree, right? So at some stage you may already find some solution, but before you find that solution, you may already go very far, right? So this is the maximum layer you have explored. So maximum length of any path in the state space. That's the idea. So you think about length because you can only go further. You cannot go this way, right? So like this is just the maximum length of any path in the space, in the state space. Okay. So you can think about the maximum layers, but of course maybe more accurate is just like the maximum length. Okay, maybe use this one is more accurate. The maximum length of any path in the state space. Okay, that means from the initial state to another state. The longest path has the maximum length m. So that will be the answer for this one. Okay, let's continue for the next. So we want to use the previous items for the variables to do the analysis of the algorithm. So the first is the BFS. So we have covered the BFS and DFS. So we look at the BFS first. So whether it's complete or not. Complete means if there's an answer, whether finally you can reach that answer. If there's a solution, right? Layer by layer, layer by layer. If you have only finite number of layers, definitely you will reach that one, right? So this is yes, if branching vector B is finite. So if it's infinite, that's not possible. So that's because you cannot exhaust one layer, maybe, right? At least some layer. B is the maximum number of children. Maybe in there's some node which has an infinite many nodes. Then you cannot finish. Infinite means you cannot finish. Infinite. So as long as the branching vector B is finite, then it's complete. This is the only condition. So that means finite. That means there's always you can find a bound for this B. Okay, and the B is less than that bound. That means finally you can finish any children, all the children of a node. So this is complete. And then optimal. If we found a solution, what is optimal? Same, if this one maybe don't care, because we visit layer by layer. We said you must explore all the nodes in the shallow layers and then to the next layer. So that, of course, so you find a solution that will be the shallowest solution. Shallowest solution. So that means yes, if cost is equal to 1 per step, that means each move, for example, from one node to the next node, the cost is the same. It's a unit, just like this. It's a unit. But if, for example, this is lot unit, for example, like we said, is from New Orleans, from Long Beach to New Orleans. This is the cost. The cost is the weight. Is just the distance between two cities. Then we cannot use that one, because when we said it's layer by layer, we just think about this is the same as this one, this same as this one. So the path will be just based on the layer, But if it's not, for example, this is 5, this is 1, they are different. So though they are the same layer, but they have different weights, they have different paths. So we cannot say this cost is the same as this one, So this is the only condition. So that's why we mentioned we have two groups: breadth first search and deep depth first search, and the iterative deepening first search. They are the same group. So same group is here. That means they have the same step cost. If like that, we can consider BFS, DFS, or IDS. Okay. Next one is the time. So we set the number of nodes which has been generated. We decided the time. So you explore the layer by layer. So we need to consider for the search tree how many nodes you have been visited. So we already know the best answer. The M is the maximum length, and the D is the optimal solution. We mentioned here D, depth of the optimal or shallowest solution. So that means we already know here is D. So you can only till here you will stop, because you will find the solution. So this is the idea. Then how many nodes you can explore? So it's easy, because already have the branching factor is B, and then at most you have B nodes in this layer. Because this one is the maximum number of children. So this is 1, and then this is the B at most as 1. They have B and also b. So b by b is b square until the end, okay, depending on layer. So this layer is d, this layer, so b to the power of d. If layer 1, this is layer 0, layer 1, okay, if we sum that, that's the b to the power of d. So all the nodes you have explored, then just add them together. So you know this is a sequence, okay? 1 plus b square plus tier bd. In fact, this one we can write, this is b to the power of 0. So it's 1 minus bd plus 1, and then 1 minus b. So in fact, this one, this is a constant. So in fact, you can just minus 1 put here, okay? Minus 1 put here. Constant can include. So divide this one, you got a b to the power of d. So that's will be the solution, right? B to the power of d will be the final solution, okay? D is the depth of the opening solution. And then space is the same as the number of nodes you have visited, so it's the same, right? Time means space, okay? Always that same. So because that's the number of nodes you have visited, maybe only the difference is like a constant difference. So that means how many bytes you need to save one node, okay? So this is the number of nodes, b to the power of d. At most, is big O, okay? Big O of d. Big O of b to the power of d. And then space is the bigger problem for our concern, because time, as long as you have a powerful computer, okay, you can do that. But usually memory is less than time, okay? The probability of a CPU. You can you explore nodes that will be very quickly. But saving the nodes, we know node itself also contain some other information. You take space to store it, okay? Path, parent, and some other additional, for example, each cell, what's the state of that node. So that means this is the main concern, right? Space is the big concern. So you may need to consider if the memory is not that big, and also the problem is big. For example, B is branching factor is very big, and D is also maybe very big. For example, the solution is very deep, and the branching factor is also big. Then b to the power of d will be very big value. So you may need to have a lot of memory to save the nodes temporarily, right? So this is the idea, because later you need to reconstruct the path for the solution. Okay, let's look at the DFS. What's the difference between this one and that one? So first one is complete or not. If there is a solution, whether we can reach that solution. For this one, we can only say don't know, okay? It depends. We mentioned before, it has a limitation. If you explore here forever, then you have a low chance to reach the solution. So this one, we can only say if it's finite depths, we can reach the end, and then we can find a solution. If it's infinite, okay, for example, some space, some paths, there's infinite depths, then maybe no, okay? So fails in infinite depths spaces with loops as well, okay? Loops go further and further till you cannot return. You have a loop, okay? We can modify this one to avoid repeated states along the path. We can complete infinite spaces. That's first one is avoid repeated states, okay? And then can kill this one, and then kill this infinite. We can complete in infinite spaces. So that means if it's infinite, we may reach some boundary. We'll go back, okay? So that means we still have a chance to find it, but we cannot guarantee, okay? Because we don't know. So you must set a good threshold for you to reach the depths, okay? So this one till, for example, you reach the maximum possible depth, you need to go back. So this will make the search complete, because this one is a bound. If you really need the bound, there's no problem. Okay, next one is optimal or not. So even you can find the solution, but we don't know whether this is optimal, because you cannot prove this is the shallowest. Okay? Optimal must be the shallowest. So this one is no. Returns the first solution to find, but cannot guarantee it's the shallowest. Time is how many nodes you have visited. So for here, you need to use the M, okay? The M is the longest path, and then for each one you have the branching factor is B. Okay, so this is B to the M. Could be the time to reach a solution at a maximum depth M. So all the possible. So at most is B to the M. So why is B to M? You can just add cut. So this is 1. Okay, should be similar to preferred cut 1 and then B and then possible cut B and then B square till the end, and then you reach the M. That's the maximum. So you add this all of them together. 1 minus B M plus 1 minus B. So add this 1 plus B to B square to this one. So cancel out the 1B. So you get B to the M. So space will be the same cut. Terrible if M is much larger than D. Much larger than D. That means like the 2 to the power of 100. Okay? For example, like this one will be very big. Okay. But if there are lots of solutions, maybe much faster than BFS. So that means lots of solutions means it's very possible for you to find the solution quickly, right? Because the solutions were scattered in many different layers, so it can be faster than BFS, especially if the solutions are in the deeper layers, because the BFS must visit layer by layer and then can reach the solution. Space is not same. Okay? So here you save. That's maybe the reason is here. You only need to save. You don't need to save all the branches here. You just each one cut. It's just layer by layer, and save this. This one should be okay. So BM. Each maximum is depth is M, and then you have branching factor B. That means you just need to save only this number, because you don't need to keep all the others. Okay? Just only this one branch. Okay? That's maybe the difference between this one. So for the BFS, they are the same, but DFS, this is a difference. Okay, this difference. You can save space for this method. So because you explore only on one depth, you don't need to save all the nodes in that layer. So the branching factor will only factor a single line, not just all the layers. And then so maybe we can continue for the rest for the next week. But overall, next one we'll talk about improved algorithm for depth first search. So we said use DFS. We may not be able to find the solution, but here we want to improve it. So we can just each time we just deeper the search threshold. We don't want to search all the depths. We just search one each time one, and then if we cannot find one, we add it. So this is the idea. layer 2, layer 3, layer 4, and so on like this. So next week we'll continue to explore. Due to the time, maybe we just leave it for the next week for clarification, just make it clear for you. Okay, but BFS and DFS we already finished, so you are ready to implement the two algorithms there. So of course you need to select only one to see which one you prefer, and then select one. You can use the stack, you can use a queue to see which one is good for you. If you want to use the stack, use the DFS. If you want to use the queue, use BFS. And if you already know BFS, you want to explore DFS, that's also great. Okay, that's all for this week. I think we can only reach here and then continue next week. Okay, so just do your program assignment, and then I will prepare some homework for this one. But my plan is that since you have project for this chapter, maybe I will just give you less number for homework questions. Okay, that's all. Thank you. See you next week.